Hi guys, please take out your packet and look at page 7. It's this page. Pause the video and take out your packet. And I'm going to go through a couple of examples with you. I know that we did 1 in class, 1A. I'm going to go through B with you. I know we wrote down the need to find. If it says how fast, then you are finding the derivative with respect to time. And then how fast is the volume changing? This is what they're looking for when their radius is 1. Okay, the formula that we'll be working with, like we need something to find the derivative of. And in this case, it's the volume. So suppose that the balloon's being inflated in such that the radius r is increasing at a constant rate of 2. So this constant rate of 2, that's a derivative that they've given you. And when it says given, let's write that down. So this is telling us how quickly the radius is changing. So it's the radius, so there's the r. And because it's per second, this tells you, again, that's with respect to time. So I'm just going to grab a highlighter so you realize that this is per second. And so this also must be with respect to time. And they gave you how quickly the radius is changing. So again, we're looking to see what's a function and what's not a function. 4/3 is a constant, pi is a constant. You know the radius is a function because it's changing at this rate. So we have to do implicit differentiation for part B. And implicit differentiation, we're going to take the derivative of both sides, not with respect to x, but with respect to t. So it's the derivative of volume with respect to time equals 4/3 pi is going to just stay. And we are going to take the derivative of r squared r cubed, with respect to time. Time, r, you need implicit differentiation. Here we did not, because this was with respect to r, and then r was considered the variable in A. In B, time is considered a variable. R is not a variable, R is a function. So implicit differentiation with some chain rule. The inside function's r, its derivative is dr over dt. The outside function is cubed, its derivative is this. And then we want to throw back in the r. So here's how you know that you're in a good spot. They're looking for how fast the volume's changing. This is what we need. 4/3 is going to stay, pi will stay. They gave us, and this is why they gave us that 2. They gave you the 2 because you'll need to plug it in. 3 is going to stay. This is where you plug in this radius to be 1. At the end, 1 squared. And that ends up being your answer, and it ends up being 8 pi. And I know I didn't say provide units, but let's provide units. This is how fast the volume is changing. Volume is centimeters cubed, and it's with respect to time, and time is measured in seconds. This is how fast someone's blowing up the balloon. Okay, let's go on to C. Air is blown into the balloon at a constant rate of 50 centimeters cubed per second. Look, this is a rate. This units tell you, the per tells you it's a rate. This is the rate that volume is changing. So dV over dt, this is how quickly volume is changing. It's 50 centimeters cubed per second. How fast is the radius of the balloon increasing? Now they want the radius and how quickly it's changing when the radius is 1. So I told you how fast you're blowing up the balloon, but they want to know how fast your radius is changing. It's the opposite of this. They gave you how quickly radius was changing, and now in B they're looking for how quickly volume is changing. So it's the same volume formula that we did before. We're going to take the derivative with respect to time, and 4/3 pi, implicit differentiation. I know we've done it here, but I don't want us to use that, and we're going to start again. Implicit differentiation, r is a function because it's changing, because they want to know how fast the radius is changing. Here is dr over dt. Here's the 3. Here's the r squared. You go finish it. The only thing now is for dv or dvt, you're going to plug in 50. And this is what you're solving for. So I'll set it up, and you should go finish it. This is what you're solving for. Here's the 3, here's the 1 squared. And you're looking for the derivative of the radius with respect to time. Because the radius is centimeters and the time is second, this is what your answer is. This is really important, so please make sure you read it. I think we should write down the given and what needs to be found, what needs to be determined. That's what I recommend. You always need an equation that you're going to find the derivative of. In this situation, it was the volume formula of a sphere. In other situations, I'm going to quickly show you. In another situation, it might not be the volume of a sphere. Here, this pebble problem. This pebble problem has to do with area. It has to do with the total area and how fast the area is changing. So this will be pi r squared. Right here, this is looking for the radius of a right cylinder, and I gave you the formula. And so this is what you'll be finding the derivative of. There's a ladder problem. The ladder will make, the ladder is 10 feet long, and it's resting against a vertical line. So the ladder's at an angle because you put it at an angle because you want to climb and reach something. This right here is the wall that's vertical. So the ladder is 10 feet long, rests against a vertical wall. I think I said line earlier, sorry about that. If the bottom of the ladder slides away, so here's the bottom, right, let's think about this. Like, here's your ladder at an angle, and let's say you want to reach this point up on top. But if the ladder isn't sturdy, it's going to slide away, and if it slides away, this height becomes smaller and smaller. So again, this is your ladder right now. It reaches up to that point, but if your ladder is sliding away, this distance is sliding away, getting bigger and bigger, your ladder is going to slide down the wall. So see, you get a right triangle here. You're going to need Pythagorean theorem for this problem. All right, let's go back to my guidelines. So you'll always need a formula to find the derivative of. 3 is really important. You're going to differentiate both sides implicitly with respect to time. For these problems, it's always a race against the clock. How fast is the radius changing? Let me show you another one. How fast is the top of the ladder sliding down? At this instant. And then the instant is when the height of the liquid is h is 3. This is kind of weird. I don't know if this is a time thing, so we'll get to it when we do this. Oh, it does say with respect to time. Never mind. At this instant, what is the rate of change of the height of the liquid with respect to time? So they came out and told you that. All right, 4, and it's capitalized because students mess this up. After you found the derivative, that's when you substitute in the resulting equation all the known values. So look how I did not do anything with that 1. I did not plug in the 1 until the very end after I found the derivative here. I did not look at the radius as 1. After, this is me finding the derivative with respect to t, I did the chain rule and implicit differentiation. That's when I took this r and plugged in this 1. At the very end is when you plug in, and then you solve for whatever you're looking for. Here we're looking for volume. Here we're going to be looking for the rate that the radius is changing. And sorry, I said here you're looking for volume. You're looking for the derivative of a volume. Okay, let's go on to the next one. You should pause the video and try it yourself, and then come back and play the video and check your answer. So pebble is dropped into a pond, making concentric circles. The radius is increasing at a constant rate. Radius is increasing at a constant rate, and the constant rate is 1 foot per second. It says when the radius is 4 feet, how fast is the total area of the distributed water changing? How fast, again? So area of water, or area of these circles that are made when you threw the pebble. So here's the area formula, pi r squared. They're looking for the derivative of area with respect to time when the radius of the circle is 4. So you're going to take this equation and you are going to differentiate implicitly dA over dt. Leave the pi because it's a constant. Pull it out. The derivative of r squared with respect to t requires the chain rule. The inside function is r. The derivative of r is dr over dt. The outside function is quadratic. Here's the 2, and you throw back this r. Now you plug in the 4. You're solving for this. Pi is going to stay. I'm glad I got a derivative of radius with respect to t because they told me what it was. It's 1. 2 is going to stay. Oops, sorry. And the radius is 4. And then my answer ends up being 8 pi. Again, I'm hoping this was also 8 pi. Oh, so sorry. This wasn't 8 pi. This was, the 3's cancel. No, it is. Sorry. The 3's cancel. That is 8 pi. Okay, never mind. Yep, this is also 8 pi. Area is written as something squared. It's feet squared. And time is seconds again. Okay, last one together. Number 3. Number 3, a spherical snowball is melting. If it's melting, then the radius is decreasing. And the rate that the radius is decreasing, it's decreasing at 3 centimeters per minute. So if the radius is decreasing, think about what the derivative will be. If an amount is decreasing, then the derivative is -3. They're not going to say decreasing at -3 centimeters per minute because that's like a double negative. They'll say decreasing at 3, and you need to realize if the amount or if the length of the radius is decreasing, then the derivative is negative. So in such a way that when the radius is 20, that's how quickly the radius is changing. At what rate is the volume of the ball of the snow changing at that instant? And that instant is when radius is 20. So we need to figure out the derivative of the volume with respect to time when that instant is when the radius is 20. It's a spherical snowball. It's the formula from the first page, 4/3 pi r cubed. We're going to implicitly differentiate. I think you can handle this. The only reason I wanted to do this is because the radius is decreasing, that derivative is negative. Thanks for watching. Now you can do the homework problems.